In this program, we are going to discuss chemical bonding part 2. In chemical bonding part 1, we have discussed about different types of chemical bonds and their properties. Today, we will discuss hybridization, VSPR theory, molecular orbital theory and its different important concepts. For this, we have invited Professor Sulik Chandraji in our studio. Welcome, sir, in our studio.
Thank you, Dr. Rajiv. Now, today I am going to start with the chemical part 2. Chemical part 2 includes hybridization, valence bond side electron pair repulsion theory, molecular orbital theory. Before starting hybridizations, a learner should know about the shapes of different orbitals. So, first I have to start with the shape of different orbitals. For example, you will find there is a different orientation, but we have to move to the shapes of orbitals, where we will discuss n orbital is the region of space around the nucleus within which the probability of finding the electron of the given energy is maximum. The shape of this region gives the shape of the orbital. Shape of s orbital, as you are aware that the value of L is 0, m will be 0, so the shape will be spherical because it has same orientation in all directions. So, it should be spherical shape, hence all s orbitals are non-directional and spherical symmetrical about the nucleus. The size of s orbital depends upon the value of principal quantum number n. Greater the value of n, larger is the size of an orbital. Now, p orbital have a dumbbell shaped. We will find that they have three different orientation because m will be -1, 0, +1. So, three orientations are possible, that is px, py, pz. It means the p orbital can have three possible orientation. These three p orbitals are equal in energy, means degenerate state, but differ in their orientation. Each p orbital consists of two lobes symmetrical about a particular axis depending upon the orientation of lobes. These are denoted as 2px, 2py, 2pz. Accordingly, as they are symmetrical about x, y and z axis respectively. Now, shape of d orbital. For d orbital, r is equal to 2. There are 5 values of m, namely -2, -1, 0, +1, +2. It means d orbitals can have 5 orientation. These are represented by dxy, dyz, dxz, dx square y square and dz square. The dxy, dyz and dzx orbitals have same shape, clover leaf shape, but they lie in xy, xz and yz planes respectively. The dz square orbital is symmetrical about z axis and has a dumbbell shape with a shaped electron cloud in the center. The shape with a diagonal d square y square orbital is also clover leaf shaped, but its leaves are directed along x and y axis.
We have used SPDF symbols. Why we do not use ABCD? Why we have used SPDF?
Now, as far as SPDF is concerned, they are used for sharp, diffuse, fundamental. So, they have some significance principle for P. So, they have given the name A, B, C. We cannot give these names.
Also, sir, in case of orbitals, we use the term nodal points. Generally, most of orbitals have nodal points. What is the meaning this?
Nodal, as I have told you just now, that p orbital means that have maximum finding of electron, maximum density. So, region where the finding of electron, probability of finding electron is minimum, that point is known as nodal plane. For example, if you take, I can explain that 1s orbital, we always calculate nodal plane n minus L minus 1, where n is the principal quantum number, L is the azimuthal quantum number. So, if we know the value of n, L, we can easily calculate the nodal plane, how many nodal plane will present in particular orbital. Now, hybridization is the concept of intermixing of orbitals of an atom having nearly the same energy to give exactly equivalent orbitals with same energy, identical shape and symmetrical orientation in space. The nucleant orbitals formed are known the hybrid orbitals or hybridized orbitals. Hybrid orbitals have properties entirely different from the properties of the original orbitals from which they are obtained. Orbitals involved in hybridization should have nearly, these are the silent features. orbitals involved in the hybridization should have nearly same energy. The orbitals of one and the same atom participate in the hybridization. The number of hybrid orbitals formed is equal to the number of hybridizing orbitals. The hybrid orbitals are all equivalent in shape and energy. Hybrid orbital which is taking part in the bond formation must contain one electron in it. Due to the electronic repulsion between the hybrid orbitals, they tend to remain at the maximum distance apart. The head of the overlap of atomic orbitals are sigma bonds. The sideways or lateral overlap of the atomic orbitals give pi bonds. Now, prediction of hybrid state of the atom. The hybrid state of the central atom in covalent molecule or ion species other than complexes can be predicted by the following method. As you know, H is equal to S plus half E minus V plus minus C. Here you can say H stands for hybridization, S stands for surrounding number of surrounding atoms, E is the number of valence electron, V is the, you can simply say, number of monovalent ion or double of oxygen, plus minus C explain the charge present on a particular molecule. If charge is negative, then we put plus sign. If charge is positive, we put negative sign. I'll give you the most example here. How will you calculate here? When you find out the hybridizations, there are different steps are involved. Add the number of valence electron of all the atoms present in the given molecule. Step 2, in case of a cation, abstract the number of electrons equal to the charge on the cation, and in case of anion, add the number of electrons equal to the charge on the anion. Step 3, if the result obtained in step 2 is less than 8, divide it by 2 and find the sum of the quotient and remainder. If the result obtained in the step 2 lies between 9 and 56, divide it by 8 and find the first quotient. Divide the remainder R, if any, by 2 and find the second quotient, and add all the quotient and the final remainder R2. Let the final result obtained in 1 and 2 be X. The type of hybridization is decided by the value of X as follows. Value of X 2, then hybridization sp 3, sp2, 4, sp3, 5, sp3d, 6, sp3d2 and 7, sp3d3. Now we can take some example here. BeCl2. BeCl2, you can simply, I have just given you the formula H. H is equal to, the surrounding atoms are 2, put S in place of S2, plus half, then number of valence electron, you will find here that there are 2 valence electron, then Cl2, there are 2 Cl minus 2 Cl, so you will get sp type of hybridization. Similarly, Bf3, you will get sp3 type of hybridization because number of valence electrons are 3, monovalent ion are 3 and surrounding atoms are 3, so you will get sp2 type of hybridizations. Similarly, in CH4, you will find 4 minus 4, but surrounding atoms are 4, therefore sp3 type of hybridizations. Similarly, PCl5, we can say surrounding atoms are 5, valence electron in the P is 5, then monovalent anion is 5, so ultimately you will get H will be 5. 5 means sp3d type of hybridizations. Or you can take SF6, 6 valence electron minus 6 monovalent ion and 6 are the surrounding atoms, therefore you will get H will be 6, it means sp3d2 type of hybridization. So you can calculate by using the formula. Now hybridization of some typical molecules is given over here. You will find here that sp means linear geometry, means BF2, BCl2, C2H2, CO2. sp2 means plain triangular, SO2, BH3, BF3, NO2, NO3 minus, CO3, 2 minus. sp3 ammonia, water, methane, CCl4, SiCl4, H3O plus, NH4 plus, ClO2 minus, ClO3 minus, ClO4 minus, NF3. Rather, sp3 is also found in all the oxygen acids of phosphorus. sp3d, PCl5, ClF3, SF4, XCF2, sp3d2, XCF6, XCF4, XCO4, BRF5, and sp3d3, IF7 and XCF6. Now we can move to the, because hybridizations relate to the valence cell electron repulsion theory also. Now as we know very well, the hybridization means that electron pairs should be situated or should be arranged in such a way that there should be a minimum repulsion. BSE pair theory indicates that if the compounds having lone pair of electrons, then electrons should be arranged such a way that they should have minimum repulsion, because according to valence shell electron pair repulsion theory, repulsion between lone pair will be more as compared to lone pair bond pair will be more as compared to bond pair. So if any lone pair of electrons around the central metal line, geometry will be affected.
Generally we say कि lone pair repulsion is maximum as compared to bond pair repulsion.
Yeah.
One basic reason behind this, sir?
If you take that there are two pairs are there, because they remain localized on the central metal line. Lone pair remain localized on the central metal line.
Yeah.
Therefore repulsion will take place. However, when bond is formed, the electron pair is not localized.
Yeah.
So repulsion will be less. Now valence bond theory, a method to predict the shapes of molecule from their electronic structures. Lewis structure do not depict the shape. Basic principles: each group of valence electron around a central atom is located as far away as possible from the others in order to minimize, I just told you that there should be no repulsion, minimize the repulsion. Both bonding and non-bonding valence electrons around the central atoms are considered. AXM-EN symbolize A central atom, X surrounding atoms, E non-bonding electrons, usually a lone pair. Valence electron pair repulsion theory is useful tool for predicting the geometrical structure of the main group based on the idea that pairs of valence electrons will try and avoid each other as much as possible. Electron pair count and geometry: 2 pairs on the central atom linear, 3 pairs on the central atom trigonal, 4 pairs on the central atom tetrahedral, and these are the shapes on the basis of valence shell electron pair repulsion theory. Now, as I told you, sp2 type of hybridations, there will be always 1 lone pair and 2 bond pair. For this purpose, you can calculate or you can find out the hybridization by using the same formula. I have just told you that H is equal to surrounding atoms plus half number of the valence electron minus number of monovalent ion or double of the oxygen plus minus E. E is known as charge. So by using that formula, if there are only 2 bond pairs, for example, you take SO2. In case of SO2, the hybridization will be sp2. Now, since they are the 3 orbitals are involved, when 3 orbitals are involved, it means that there are 2 bond pairs and 1 will be the lone pair. So SO2 has 1 lone pair of electrons. So you are very well aware that carbon dioxide and sulfur dioxide both have same number of atoms, but they differ in their shape. The reason is CO2 there is no lone pair of electrons, hybridization will be sp and geometry will be linear. Whereas in case of SO2, hybridization is sp2, and since it has 2 bond pair and 1 lone pair, the shape will be V-shaped. Similarly, we can explain the hybridization in ammonia and water molecule. Although CH4, ammonia and water molecule are sp3 hybridized, but if you compare the shape of ammonia and water with methane, methane is having regular tetrahedral geometry, ammonia has pyramidal shape, and water has V-shaped structure. How will you explain this? Simply we can explain on the basis of valence shell electron pair repulsion theory. Since in all the 3 cases hybridization is sp3, but in case of ammonia there is a 3 bond pair and 1 lone pair. In water there are 2 lone pair and 2 bond pair, whereas in methane no lone pair of electrons. Therefore methane will have regular tetrahedral geometry. Since ammonia has 1 lone pair of electron, if the shape is pyramidal, then electron will be arranged in such a way that there will be a minimum repulsion. So therefore ammonia has pyramidal geometry. And similarly water has 2 lone pair electrons, so electrons should be arranged in such a way that minimum repulsion, that's why is acquired V-shaped structure. Now bond angles are also affected. Now in case of methane, because it is a regular tetrahedral, bond angle will be 109.28. In case of ammonia it changed to 107, and in water it changed to 104. So as the number of lone pair of electrons increases, generally bond angle will decrease. The reason is the electrons are present together, repulsion will be there more, but in to bond pair repulsion will be less. So bond angle will decrease. Now similarly we move to the other case, sp3d3. In case of sp3d3, the different possibilities are there. Now you can say 1 lone pair and 4 bond pair. This is the one case where you find sp SF4. In case of SF4, you will find the hybridization is sp3d, but it has a lone pair of electrons. Therefore, SF4 shape will be seesaw, not regular tetrahedral. So this shape will be not or trigonal bipedal shape will be, you will find it seesaw shape. Similarly, you take ClF3 having 2 lone pair and 3 bond pair, the shape will be T-shaped. ClF3 will have T-shape, not trigonal bipyramidal. Or you can take XCF2, where you will find again sp3d type of hybridizations, but 3 lone pair and 2 bond pair. So shape will be linear. So you will find that although all these molecules have sp3d type of hybridizations, but they differ in their structures. As I have just told you, the PCl5 is a regular trigonal bipyramidal, SF4 will have seesaw structure, ClF3 will have T-shaped, and XCF2 will have linear geometry. Similarly, we can move to the octahedral geometry, sp3d2 type of hybridizations. Again, the possibility is compound will have 1 lone pair and 5 bond pair, for example BRF5. You will find hybridization is sp3d2, but since it has 1 lone pair electrons and 5 bond pairs, so geometry will not be octahedral, rather geometry will be square pyramidal. Similarly, you can take XCF4, it has 2 lone pair and 4 bond pair, therefore geometry will be square planar, not octahedral. So you should be clear that valence shell electron pair repulsion theory, we can decide the geometry because we should arrange the electron in such a way that there should be a minimum repulsion. That's why distortion will take place, or you can say distorted structures are there.
Sir, while discussing about the structure and shapes, what is the basic difference? Suppose we have to write the structure and the shape of a molecule. How we decide which one is shape, on which property it is shape, or on which basis we can say it has a structure?
Now, as far as shape and structure are concerned, structures we can define different way also. Shape will be fixed, but structure may be different. For example, I have just told you that sp3d type, the compound will show octahedral structure, but its shape will be either T-shaped, or you can simply say seesaw type of shape. The shape they are fixed, but the structure are decided on the basis of hybridization. Now, different steps are involved when we discuss the BSEPR. Molecular formula step 1, we should write down. Then loose structure step 2, electron group arrangement, then bond angles, and finally molecular shape. As I have told you that when you discuss the molecular orbital theory, there are 2 types of overlapping, either head-to-head overlapping or sideways overlapping, sideways or lateral overlapping. When there is a head-to-head overlapping, it means a sigma bond formation takes place. When a sigma bond is formed, then there is a head-to-head overlapping. But when the sideways overlapping is there, then you will find that pi orbitals is formed. Now, if you compare the sigma bonding and pi orbitals, you will find that sigma orbitals are stronger as compared to pi orbitals. So, I will give you the little bit about this molecular orbitals. When 2 atoms come close to each other, what happens to the orbitals of each atom? You are very well aware, one s atom of hydrogen, another hydrogens, they overlap to each other and to form a nuclei. That is, you can say, bonding molecular orbitals. A bond between 2 atoms in which the electron density of the molecular orbital is between the 2 nuclei is called a sigma bond. Now, atomic orbitals can mix together to give new sets of molecular orbitals. One molecular orbital is formed for each atomic orbitals used. Orbitals are wave functions. Wave functions contain mathematical terms that can have positive and negative values. An s orbital value can either be less than 0 or greater than 0. The 2 lobes of p orbitals are separated by a node and have opposite sign. Here I will tell you one thing, that most of the students or teachers confused when they put negative or positive sign, they considered there should be repulsion. But that is not repulsion, that is the sign of wave functions. So molecular orbital will form only when the sign of wave functions is same, plus plus or minus minus. It does not mean the repulsion will take place. So most of the students and teachers confused that there should be repulsion. Now you will see here different color represent opposite mathematical sign. Now there are 2 different colors are there. So you will find one is the violet color One is the other is the blue color. Violet color indicate positive sign, blue color indicate negative. PZ, py orbitals overlap. This is overlap has given sigma bond formation. Now these are different type of overlapping, PZ. This will get overlapping. You just see, this is the animation. Now anti-bond formation. Now when I told you the MO theory, you should be clear there are three conditions. First condition is the atomic orbitals should have almost same energy. Second is their wave function should be same. Sign of wave functions, I am repeating again, the sign of wave function does not mean that negative assembly takes place. There should be always, we can say, same symmetry, and extent of overlapping should be maximum. When two atoms combine together to form two different molecular orbitals, one having lower energy as compared to atoms and other having higher energy as compared to atoms. The molecular orbital which have lower energy as compared to combining atoms is known as bonding molecular orbital, and the molecular orbital which have high energy as compared to combining atomic orbitals is known as anti-bonding molecular orbitals. The number of molecular orbitals will be same as the number of atomic orbitals overlap to each other. Now molecular orbital theory. So as I just told you that bonding and non-anti-bonding molecular orbitals. Third category is also non-bonding molecular orbitals. I will discuss this later on. Now as you are aware that we considered a homonuclear and heteronuclear molecule. Suppose you want to prepare this S2 molecule is stable or not, you can explain on the basis of molecular orbital theory. Now when two hydrogen atoms combine together to give two molecular orbitals, this is called as sigma 1s and sigma 1s antibonding. Sigma 1s have lower energy as compared to combining two hydrogen atoms, so that will be bonding molecular orbital. And another sigma antibonding having high energy, so that is called antibonding molecular orbital. So both H have one electron. So you put one electron in each atoms, then you will find the two electrons enter into the bonding molecular orbitals. So we can calculate bond order. Bond order will be equal to half number of electrons in bonding molecular orbitals, that is generally represented by NB, minus number of electrons in anti-bonding molecular orbitals, we represent it as Na. In case of hydrogen, you can simply say, since there is no electron in anti-bonding molecular orbitals, but two electrons are present in bonding molecular orbitals, so bond order will be 2 by 2, that is 1. So H2 molecule will be formed. Similarly, we can explain this if you want to say about the noble gases. Noble gases do not form a molecule. This question can be asked. So noble gases do not form a molecule. You can explain on the basis of molecular orbital theory. Because helium you can take. Helium has 1s2 electronic configurations. So two helium will have 1s2 and 1s2 means 4 electrons. So when you fill up the 4 electrons in bonding and anti-bonding molecular orbitals, 2 electrons enter into the bonding and 2 electrons enter into the anti-bonding molecular orbitals. Therefore 2 minus 2, 0. Bond order is 0, so He2 molecule will not form. You can simply say Li2 also, but the question arises about the Be2 and Ce2 molecule. Now initially the energy level diagram has been suggested sigma 1s antibonding, sigma 2s antibonding, sigma 2px bonding, then pi 2py is equal to pi 2pz, then pi 2pyz is equal to pi 2pz antibonding, then sigma 2px antibonding. When you fill up the electrons in this way, it has been found that carbon is found to be parametric and boron is found to be diamagnetic. But on the basis of experiment, reverse results were obtained. For example, that B2 is found to be parametric and C2 found to be diamagnetic. Therefore, on the basis of experiment, the energy level diagram up to nitrogen has been changed. So up to nitrogen, we should say sigma 1s antibonding, sigma 2s antibonding, then pi py is equal to pyz, then sigma 2px, then pi 2py is equal to pi 2pz antibonding, then sigma 2px antibonding. But after nitrogen, the energy level diagram will be the same as sigma 1s antibonding, sigma 2s antibonding, sigma 2px, pi 2py is equal to pi 2pz, then sigma 2px anti-bonding, etc. So we can explain the structure of all the molecular energy diagram for all the molecules of homoatomic. For example, oxygen. Now here we can also explain the parametric or diametric character. Now oxygen molecule is parametric because it has two unpaired electrons in pi 2py and pi 2pyz anti-bonding molecular orbital. But other fluorine, nitrogen, etc., they don't have any unpaired electrons. That's why they are diamagnetic in nature. Similarly, we can explain the stability of different molecules. For example, we say O2 plus, O2 minus, and O2. If we compare the stability of these molecules, you should be able to find out the bond order. Now, here I am telling you one thing here, that the student can easily explain the stability of a particular molecule. If he is going to add the electron in bonding molecular orbital, then its stability will increase. If he is removing the electron from the bonding molecular orbitals, stability will decrease. Similarly, if we remove the electron from anti-bonding molecular orbitals, its stability will increase. If we are going to add electron in the anti-bonding molecular orbitals, then its stability will decrease. For example, you take O2 plus. Now, in case of O2 plus, we are removing the electron from anti-bonding molecular orbitals. Therefore, bond order will increase, that is 2.5. The stability will increase. O2 2 minus, that is peroxo, since we are adding two electrons in anti-bonding pi orbitals, so stability will decrease. So peroxo compounds are not so stable. So similarly, O2, if we compare the stability, then O2 plus will be more stable as compared to O2. O2 will be more stable as compared to O2 2 minus. Similarly, we can explain magnetic behavior. Now, since O2 plus has one unpaired electrons, O2 has two unpaired electrons, and O2 2 minus has no unpaired electrons. So therefore, O2 2 minus will be diamagnetic. O2 and O2 2 plus will be paramagnetic in nature. So you can explain. Similarly, we take the heteronuclear atoms, then energy diagram will be somewhat different. Not in the electronic configurations, but in the shape. Actually, there are two different atoms. We have already explained polar and non-polar. So these heteronuclear molecules have polar character. So therefore, atom which have more electronegativity will be situated at a lower energy, and atom which have high energy will be situated at a high energy. So if you explain the molecular diagram for carbon monoxide, you say that oxygen unsymmetrical. You will find oxygen, I will show you, this is the case of carbon monoxide. You will find here that they are sp hybridized. Carbon electrons belong to the anti-bonding molecular orbitals and oxygen electrons belong to the bonding molecular orbitals. So we can say that if we molecular diagrams, we explain the heteronuclear, then its shape will be different. So that's about the chemical bonding.
Learners, I am sure that you have got the basic idea about the VSPR theory, molecular orbital theory, and the hybridization. These topics are not only important for your class 11-12 study, but also very important for the competitive examinations. You can see every year's IIT or medical paper, you will find definitely 3 or 4 questions from this topic. So you just keep on revising all these topics, basically VSPR theory, molecular orbital theory, and hybridization. They are the most important for the competitions. Thank you, sir, for coming in our studio.
Thank you.